Welcome to acid-base titration. So first, let's start with the titration of a strong base with a strong acid. Now, using an acid-base titration curve, we can determine the quantities and pKa values for acidic and basic substances in solutions. Now, we're going to examine various acid-base titrations, and in each case, we will construct a graph showing how the pH varies with the volume of titrant added. Now, we will start by writing the chemical reaction between the titrant and the analyte. Now, remember, the analyte is what we have in the flask, and then the titrant is what we have in our burette. So that's what we're adding. So we're measuring the volume of titrant that we have to add in order to react with our analyte. So again, we're going to start by writing the chemical reaction between our titrant and analyte, and then we will calculate the composition and pH after the addition of some volume of our titrant. So first, let's examine the titration of 50 milliliters of 0.02 molar potassium hydroxide with 0.1 molar hydrobromic acid. Now again, first we need to write the chemical reaction. The reaction between our titrant and analyte is given here. We have hydrogen ions plus hydroxide ions react to yield water. Now again, we can ignore the potassium ions in the potassium hydroxide, and we can ignore the bromide ions in the hydrobromic acid because potassium hydroxide is a strong base, so the potassium and hydroxide ions will dissociate completely, and hydrobromic acid is a strong acid, which means the hydrogen ions and bromide ions will dissociate completely. And that means that we can ignore the potassium ions and the bromide ions because they aren't actually going to be involved in the reaction. Now, we know this equation is simply the reverse of the autoionization of water, and that means that if we look at the K value, the equilibrium constant for this reaction, then that equilibrium constant is going to be equal to the inverse of Kw, because our reaction is the reverse of the autoionization reaction. And because we know that Kw is equal to 10 to the minus 14, that means that our K value here is going to be 10 to the positive 14. Now note that this value of 10 to the positive 14 is so high that we can certainly conclude that the reaction goes to completion. That is, this arrow here is a single-headed arrow. It's only pointing to the right, indicating that this reaction goes to completion. If we have virtually any hydrogen ions or hydroxide ions around, they're going to react together to give us water. Now, we know that that's not strictly true because we know that we will never have a zero concentration of either hydrogen ions or hydroxide ions so long as we have water around, but if we have a sizable concentration of either hydrogen ions or hydroxide ions, then the concentration of the other one is much, much smaller. So the volume of hydrogen bromide, our titrant, that is needed to reach the equilibrium volume, VE, can be calculated because the number of moles of hydrogen bromide must equal the number of moles of potassium hydroxide, because our hydrogen ions are reacting with our hydroxide ions in a 1-to-1 mole ratio. And we can calculate that. So we've got VE, which again is our volume at the equivalence point, and once we work out the math, that works out to 0.01000 liters of hydrogen bromide added, so 10 milliliters. And therefore, the equivalence point occurs when we have added 10 milliliters of our titrant hydrobromic acid. Now we can split up our subsequent calculations into a few different regimes. Before we add our 10 milliliters of hydrobromic acid, then we have an excess of hydroxide in solution, and that means that the pH is high. After we've added 10 milliliters, and we've continued to add a little bit, then we have an excess of hydrogen ions around, because now we've reacted away all of our hydroxide ions, and we have some excess hydrogen ions present, and that means that the pH is going to be low. Now, at exactly 10 milliliters of our hydrobromic acid added, that is, at exactly the equivalence point, then we have added exactly equal amounts of our acid and base. We have exactly equal amounts of hydrogen ions and hydroxide ions in solution, and that means that the pH is equal to 7, because we have nothing in solution that acts as an acid or a base other than water. That is, at the equivalence point, the only things that we have in solution now are water, our solvent, the bromide ions left over from the hydrobromic acid, and the potassium ions left over from the potassium hydroxide. Now, because potassium hydroxide is a strong base, that means the potassium ions are a negligible acid, that is, they won't affect the pH, and likewise, the bromide ions won't affect the pH because hydrogen bromide is a strong acid, and therefore the bromide ions are a negligible base, and thus we have nothing that will change the pH away from 7. Now, we could essentially have created this solution by simply adding potassium bromide to water. Potassium bromide is neither an acid nor a base, and that means the pH after adding the potassium bromide would be exactly the same as it was before adding the potassium bromide, which would be 7.0. Now, one thing you need to keep in mind here is that while we're trying to find the equivalence point during our titration, that's not what we actually determine. During our titration, we actually are determining the end point. So remember, the difference between these two is that at the equivalence point, we have added exactly equal quantities of our two reactants. For an acid-base reaction, that's going to be equal quantities of acid and base. Now, the end point, on the other hand, is that point at which we can determine that the reaction has completed. And the position of that endpoint is going to be determined based upon how you are detecting the endpoint. For example, if you are using an indicator, that indicator is going to change color at some pH range, and that pH range is not necessarily going to match up exactly with your equivalence point. Now, that pH range needs to be past the equivalence point, but you want it to be as little past the equivalence point as possible. For a strong base being titrated with a strong acid, the equivalence point will have a pH of 7.0, and that means that we want to be using an indicator that changes color roughly 1 to 2 pH units beyond the equivalence point, which means in this case we're going to start with a high pH because we have a base initially, and at the equivalence point we're going to be at 7.0, and that means we want our acid-base indicator to be changing color at a pH of roughly 5 to 6. So let's examine each of our three regions of our titration more closely. First, we're going to look at before the equivalence point. For example, if only 3 milliliters of our hydrobromic acid have been added to our solution, then the total volume is 53 milliliters. Now, the hydrobromic acid is consumed by the potassium hydroxide that we have in our flask, and we still have excess potassium hydroxide. Now, the moles of hydrobromic acid added, we can calculate, and we end up with a value of 3.00 times 10 to the minus 4 moles of hydrobromic acid added. Now, that number of moles of hydrobromic acid added will react with our potassium hydroxide, and so we'll have less potassium hydroxide than what we started with by 3 times 10 to the minus 4 moles. So let's figure out how many moles of potassium hydroxide we started with. Well, we know that we started out with 50 milliliters of our potassium hydroxide. We know the concentration of potassium hydroxide was 0.02 molar, and that means that we had 1 times 10 to the minus 3 moles of our potassium hydroxide. Now, once we've subtracted the number of moles of potassium hydroxide that have reacted away, then we get a value of 7.0 times 10 to the minus 4 moles of potassium hydroxide that are still present in solution. In other words, we know that the equivalence point is at 10 milliliters. We've added 3 milliliters, so we're 30% of the way to our equivalence point, and that means we should have reacted 30% of our potassium hydroxide, which means that we should have 70% left, and that is in fact what we found. We did in fact have 70% of our initial value of potassium hydroxide still present. And now we can calculate the hydroxide concentration. Now, this value is not going to be simply 70% of what it was initially, because we have changed the volume of our solution. So the hydroxide ion concentration is then the number of moles of our potassium hydroxide divided by the current total volume of solution. And that's going to be 7.0 times 10 to the minus 4 moles divided by 53 milliliters, which when we convert to liters is then 0.05300 liters. And that gives us a hydroxide ion concentration of 0.0132 molar. And then using the concentration of hydroxide present in solution at this point, we can then calculate the concentration of hydrogen ion present and the pH. The hydrogen ion concentration is then 7.57 times 10 to the minus 13 molar, and that gives us a pH of 12.12. However, we can streamline this calculation. When we've added 3 milliliters of our hydrobromic acid, then the reaction is 30% complete, and that means that we have 70% of our potassium hydroxide remaining. Now, the concentration of our remaining hydroxide must be corrected for the dilution that occurred upon adding those 3 milliliters of our hydrobromic acid. And so if we take then the fraction of our potassium hydroxide that remains, which is our 10 milliliters minus the 3 milliliters that we would have reacted away, divided by the initial amount of 10 milliliters, that's going to give us a fraction of 0.7 times our initial concentration of potassium hydroxide, which was 0.02000 molar. And then correcting for the dilution, we then have 50 milliliters divided by 50 milliliters plus 3 milliliters, so the total volume now of 53 milliliters. So we're going to have 70% of our initial concentration, and then corrected for the dilution, this fraction is going to be a little less than 1. That then gives us a value of 0.0132 molar. Now again, the first term here, this first set of parentheses, is then the fraction of hydroxide ion that remains after we've added our 3 milliliters of hydrobromic acid. The second term here is our initial concentration of our potassium hydroxide before we began the titration. And then our third term here, this fraction, is the dilution factor. And then we can go ahead and calculate the pH. Again, we have a hydrogen ion concentration of 7.57 times 10 to the minus 13 molar, and the pH is 12.12. Now, we will use this simpler method in the rest of our calculation. We've already proven that it works just fine, and it's simply faster, so that's the calculation that we're going to use in the rest of our calculation. So let's move on to the second domain, which is at the equivalence point, at exactly the equivalence point. So at the equivalence point, we have added exactly the same quantity of our hydrobromic acid as potassium hydroxide. And this means that we essentially have a solution of potassium bromide. And this means that the pH is determined by the autoionization of water, and the pH then is 7.00, provided that we're at a temperature of 25 degrees C. Now note that the pH at the equivalence point is only equal to 7 when both the titrant and the analyte are strong electrolytes. Now let's turn to our third domain, which is after the equivalence point. After the equivalence point, we are adding excess hydrogen bromide to our solution. Now, the concentration of excess hydrogen ions at 10.50 milliliters is our concentration of our hydrobromic acid, 0.1 molar, times the excess hydrogen bromide we have left over after the initial 10 milliliters has reacted with our potassium hydroxide. That is 10.5 milliliters minus the 10.0 milliliters that reacted away, divided by the total volume now, which is our initial 50 milliliters plus 10.50 milliliters. And that then gives us a hydrogen ion concentration of 8.26 times 10 to the minus 4 molar, which gives us a pH of 3.08. So the first term here is the concentration of our hydrobromic acid. The second term is then the excess volume of our titrant divided by the current volume, that is the dilution factor. So the titration curve that's shown here shows how rapidly the pH changes near the equivalence point. That is, initially the pH doesn't change much because we haven't reacted away very much of our potassium hydroxide yet, and then when we get close to the equivalence point, the pH changes much more rapidly, and just after the equivalence point, the pH changes very rapidly. But then once we've added a sizable amount of hydrogen ions in excess, then for every little bit more hydrogen ion that we add, we're changing the total amount by a smaller and smaller fraction, and that means past the equivalence point, our titration curve levels off again. Now, the equivalence point is where the slope, our first derivative of our titration curve, is the greatest, and where the second derivative is 0. Now, this is going to be true at what we call the inflection point. That is, initially, our titration curve is curving downwards, and then at some point, it begins to curve back upwards again. And so if we are looking at the first derivative of our titration curve, we're going to have a negative value all the way along, but the second derivative is going to have a negative value for the first part, and then on the second part, past the equivalence point, it's going to have a positive value, but our second derivative is going to be equal to 0 at our equivalence point. Now, note that the equivalence point is only at a pH equal to 7 when both the titrant and the analyte are strong electrolytes. If either one of them is a weak electrolyte, then the pH at the equivalence point will not be equal to 7. For example, if we have a strong base and a weak acid, then at the equivalence point, we will have the conjugate acid of our strong base, which will be a negligible acid, and we will have the conjugate base of our weak acid, which will be a weak base. And that means that in that case, our pH will be that of a weak base. It will be somewhat above 7. We will have an alkaline solution left over. So now let's examine the titration of a weak acid with a strong base. We're going to use 2N-morpholino ethane sulfonic acid, which we're going to symbolize MES, and MES has a pKa of 6.27. We're going to titrate that with our strong base, sodium hydroxide. So let's titrate 50 milliliters of 0.02 molar MES with 0.1 molar potassium hydroxide. Now note that MES is the protonated form, and we're going to symbolize that as HA. So in our stylized reaction, we have HA plus hydroxide yields A minus plus H2O, and then down here, we've got the structure of MES. Now, note that the equation that I just showed is simply the reverse of the base hydrolysis reaction, and that means that the equilibrium constant for the reaction that I showed is K, which is equal to the inverse of the equilibrium constant for the base hydrolysis, that is K equals 1 over Kb, and we know that Kb is equal to Kw divided by Ka, and that then gives us our equilibrium constant K is equal to Ka divided by Kw, and that gives us then a value of 5.4 times 10 to the 7. Now, because this is a positive exponent, 10 to the positive 7, that means that our reaction goes to completion. Now, the volume of sodium hydroxide necessary to reach the equivalence point can then be calculated here. We have VE, the volume at the equivalence point, is equal to our 50 milliliters of MES times the initial concentration of our MES times the mole-mole ratio, which is 1 to 1, and then divided by the concentration of our sodium hydroxide, which gives us then a value of 0.01 liters or 10 milliliters of sodium hydroxide that we have to add to get to the equivalence point. So now we have 4 regions to examine. The first is before any base is added at all, and in this case the solution then contains our acid in water. The second region is after we've added some base but before reaching the equivalence point, in which case we have a mixture of HA and A minus. The third case is at exactly the equivalence point, in which case nearly all of our HA has been converted into A minus. And then our last case is after the equivalence point, in which case we have excess hydroxide added to our solution of A minus. Now, before any base is added, the solution contains HA in water. Now, this is a weak acid solution, and the pH is then governed by the acid dissociation equilibrium, which I've shown here. In the second region, after we've added some base, but before we've reached the equivalence point, then we have a mixture of HA and A minus, and that means that we have a buffer solution, and we can use the Henderson-Hasselbalch equation in order to find the pH. Now, at the equivalence point, then remember that nearly all of our HA has been converted into A minus, the deprotonated form, and this is then a weak base solution, and the pH is governed by the weak hydrolysis reaction given here. Now note that we could have made an equivalent solution by simply adding A minus to water. And then in our fourth regime, after the equivalence point, then excess hydroxide has been added to our solution of A. That is, excess hydroxide has been added to this solution that we could have made simply by adding A minus to water. Now, because we have excess hydroxide ions present from adding excess strong base, we can then neglect the effect of the hydroxide ion here from the base hydrolysis of our A minus, of our weak base. In other words, we're going to treat this solution as if we were adding that excess hydroxide ion simply to water. In other words, after the equivalence point, it essentially doesn't matter that we have some weak base left around, because once we're adding strong base, the hydroxide from our weak base is negligible. So let's plug in some values to each of our cases here. Before we've added any base, we have a solution of 0.02 molar HA, and this is then a weak acid problem. We know how to solve these problems from earlier chapters, and that means that we have a hydrogen ion concentration of 1.03 times 10 to the minus 4, which gives us then a pH of 3.99. Now, once we add some of our hydroxide ions, then we have converted some of our HA into A minus, that is, we've deprotonated some of our acid, and we now have a buffer solution because we have a weak acid and we have its conjugate weak base. And this means that then we can use the Henderson-Hasselbalch equation in order to find the pH. And this means that we just need to find the ratio between the base concentration and the acid concentration. So let's look at an example where we've added 3 milliliters of hydroxide. Let's start by making an ice table where the values are relative to the initial concentration of HA. So our initial concentration of HA is all of our HA, and that means we have a value of 1. We will have reacted away 30% of it, so that concentration will change by negative 0.3. We will then have 0.7 remaining. Our hydroxide, we would have added 0.3. All of it will react, we'll have none of it left. Our A minus would have started out with nothing initially. We will have made 0.3 through our reaction, and that means we will end up with 0.3. And then our last term here, the product of water, we can ignore that because we know we have lots of water around, so the concentration of water is essentially unchanged. And this means that we can now find the pH. We have the Henderson-Hasselbalch equation here. We can plug in our pKa of 6.27, and we can plug in our ratio of 0.3 to 0.7, which gives us then a pH of 5.90. Now let's examine a special case where we've added exactly half of the required volume of our base, once we've added 5 milliliters of our sodium hydroxide. In this case now, we started out with 1 HA. We now have half of it left because we reacted half of it away. We reacted away all of our hydroxide, and now we have half of our acid in the base form, in the deprotonated form. And now when we plug these values into the Henderson-Hasselbalch equation, now that ratio between the concentration of base to the concentration of acid, because those concentrations are equal to one another, that ratio is equal to 1, and that means that the pH is simply equal to the pKa, because the log of 1 is 0. And so in this case, the pH would then be equal to 6.27. And therefore, the midpoint of our titration, that is, when we've added half of VE, half of our volume at the equivalence point, then the pH is equal to pKa. Now, note that this ignores the activity coefficient, so it isn't strictly true, but it's a reasonable approximation in many cases. Then in our third regime, at the equivalence point, we have added exactly as much base as we had acid. That means we have deprotonated virtually all of our HA to the A minus form. And this means that we now have a solution that contains only our weak base. In other words, we have a solution that we could have simply made by just adding our A minus, our weak base, to the solution. We know how to solve an equilibrium problem involving a weak base. Now, note that we have to correct our concentration here for the fact that we have diluted the solution. Once we put in our dilution factor, we get then a smaller formal concentration for our base than the initial starting concentration of our acid, and we end up with a hydroxide ion concentration of 1.76 times 10 to the minus 5 molar, which gives us a pH of 9.25. Now note that the pH is not 7.00 at the equivalence point. It was 9.25. Now, the pH at the equivalence point for the titration of a weak acid with a strong base will always be above 7 because we now have a solution that contains the conjugate weak base of our acid. And in our fourth regime, after the equivalence point, at this point now, we are adding hydroxide to a solution of our weak base, A-, and the hydroxide is a much stronger base than our A- is, and our weak base. And this means we can neglect that base hydrolysis of A- and simply look at the excess hydroxide ion concentration to find the pH. So let's calculate the pH when we've added 10.1 milliliters of sodium hydroxide. In this case then, the hydroxide ion concentration is equal to 0.1 molar. Our concentration of hydroxide ion times our dilution factor, 1 times 10.1 milliliters minus 10.0 milliliters, in other words, the excess volume of sodium hydroxide that we've added, at 0.1 milliliters, divided by then the total volume of solution, which is 50 milliliters plus 10.10 milliliters, or 60.1 milliliters. That then gives us a hydroxide ion concentration of 1.66 times 10 to the minus 4 molar, and then calculating the pH from there, we get a pH of 10.22. So let's take a look at the titration curve. I've plotted over here the titration curve for the titration of a weak acid with a strong base. Now note that the equivalence point, that inflection point, is not at a pH equal to 7. Because pH equal to 7 is here, but the equivalence point is up here, above a pH of 9. Also note that the pH is equal to the pKa at the half equivalence point. Because again, at that point, we've added equal quantities of strong base to our weak acid, and that means we have equal concentrations of our weak acid and its conjugate weak base. At that point then, the pH is equal to the pKa. So initially, the pH is low, and the pH changes quite rapidly until we set up our buffer situation. That is, once we've converted a significant fraction of our weak acid to its conjugate weak base form, now we have a buffer solution, and then the pH is not going to change nearly as rapidly until we get very close to the equivalence point, in which case we have essentially used up all of our buffer capacity. We've converted almost all of our protonated form to the deprotonated form, and that means that as we react away just a little bit more of our protonated form, we're changing that ratio from deprotonated form to protonated form by a lot, because even by adding just a small amount of our base and deprotonating a little bit more of our acid, we're changing the total amount of our protonated form significantly. And last then, after the equivalence point, the curve is nearly identical to that for the titration of a strong acid with a strong base. In other words, past the equivalence point here, we can basically ignore the contribution from our weak base because we have some strong base around. And now let's look at the shape of that titration curve as we change the strength of our acid. As the acid becomes weaker, the inflection point becomes shallower and shallower. So if you note, this bottom curve here is a strong acid, that's this blue one. If the pKa is equal to 2, then we have this black curve that's just above it. Then we go to pKa of 4, 6, 8, and 10. And you note that as the acid becomes weaker, then that inflection point becomes less vertical, such that at a pKa of 10, it's very difficult to discern that inflection point there compared to the inflection point here from when we've set up the buffer, that is the half equivalence point. And if we turn to the second graph over here we have plotted different concentrations of our acid, where the acid strength now is not changing anymore. And so before the equivalence point, then the higher the concentration of our acid, the lower we will be on the pH axis. And so as we decrease the concentration of our acid, then we're having a higher value on the left side before the equivalence point. But then after the equivalence point, those positions are reversed. Note that here we're titrating with an equal concentration. And so as the acid concentration goes down, the base concentration also goes down. And note here that if we have a very small concentration, or if we have a concentration of just 2 micromolar, then this inflection point becomes very difficult to see. So in either one of these cases, if the titration curve has an inflection point that is too difficult for us to determine accurately, then we cannot draw any conclusions from that titration, and that means that our titration has become impractical. So we've looked at the titration of a weak acid with a strong base, and now we're going to do the reverse. We're going to look at the titration of a weak base with a strong acid. Now the titration of a weak base with a strong acid is simply the reverse of the titration of a weak acid with a strong base. That is, we still have 4 regions. Before any acid is added at all, then we have a solution of our weak base, and the pH is determined by the Kb equation. In other words, we simply have the base hydrolysis equilibrium of a weak base. We know how to solve that. We have Kb is equal to x squared divided by F minus x. In our second region, after adding some acid and before reaching the equivalence point, then we have a mixture of B and BH plus are deprotonated and are protonated form, and that means that we have a buffer, and we can then calculate the pH using the Henderson-Hasselbalch equation. Now note here that you have to use the pKa for BH plus, and you're still putting the base concentration divided by the acid concentration. Now at the equivalence point, we have added enough acid to convert all of our B, our base, into BH plus, the protonated form, that is the conjugate acid, and therefore we now have a solution of weak acid, and the pH is then determined by the Ka equation, the acid dissociation reaction. This should be a Ka here. So the Ka is equal to x squared divided by F prime minus x. And note that we must take the dilution of the base by the acid into account, and we do it in the form of this F prime. Also note that the pH must now be below 7.0 because we have a solution that contains a weak acid. And after the equivalence point, we now have excess hydrogen ions present from our strong acid, and that means we can neglect the effect of the acid dissociation reaction for our weak acid. In other words, these calculations are all equivalent to those that we've already gone through for the titration of a weak acid with a strong base. So now let's turn to titrations in diprotic system. If we have two protons that we can remove from our acid, the principles that we've already developed for monoprotic acids can be extended to titrations of polyprotic acids. So let's examine two cases. First, a typical polyprotic base with two observable equivalence points. And next, we'll look at a polyprotic base with an equivalence point that is unobservable. Now those two are plotted over here. So the first one, where we have two observable equivalence points, is the top curve in blue, and you can see we have one equivalence point here at point C, and another equivalence point there at point D. In the second case, we have the bottom trace. There we have an equivalence point here at H, and our second equivalence point is at point J, but you can't tell that that's the equivalent. So in this case, the upper blue curve is the titration of 10 milliliters of 0.1 molar base B with 0.1 molar hydrochloric acid. And B has a pKb1 of 4.0 and a pKb2 of 9.0. And in this case, the equivalence points, which we've already talked about, are C and E, are easy to see, and those correspond to the first protonation and the second protonation of our base. Now, because the concentration of our acid and our base are identical initially, then the first equivalence point, C, is at a volume of acid added equal to the initial volume of our base, which was 10.0 milliliters. Now, the second equivalence point is then at double the volume of our first equivalence point, which is then 20.0 milliliters of acid added. So first, let's look at point A. This is before we've added any acid, and then the solution contains only our weak base B, and that means that the pH is governed by the first base hydrolysis reaction given here. We know how to solve these types of problems, so we get a hydroxide ion concentration of 3.11 times 10 to the minus 3 molar, and then a pH of 11.49. At point B, this is after adding some acid and before reaching the equivalence point. We then have a buffer that contains B and the BH plus, the intermediate form, and this means that we can use the Henderson-Hasselbalch equation for the weak acid, which is BH plus. Now note that the pKa we need to use is the second pKa for the BH2 2+. Now at point B, this is the half equivalence point, then the ratio between the concentration of B and BH plus is 1 because those concentrations are equal. And note that Ka2 is equal to Kw divided by Kb1, which is 1.0 times 10 to the minus 14, divided by 1.0 times 10 to the minus 4, which then gives us a value of 1.0 times 10 to the minus 10. That is, the pKa2 is equal to 10. And then the Henderson-Hasselbalch equation gives us a pH equal to 10.0. And again, note that the pH at point B is equal to pKa2. Now, if we want to calculate the pH at some point between A and C, that is between the starting point and the equivalence point that is not B, not the half equivalence point, then we need to determine the fraction of B that has been converted to BH plus, the fraction of our base that has been protonated that first time. For example, suppose we have added 7.5 milliliters of our acid. In this case, we will have reacted 75% of our B to BH plus, and so we will have 0.25 remaining divided by 0.75, how much we've protonated, and that gives us a pH equal to 9.52. Now let's look at point C. This is the first equivalence point. So here, at our first equivalence point, we have converted all of our B into BH plus, which is the intermediate form of the diprotic acid BH2 2+. Now remember from chapter 9, we know that the hydrogen ion concentration is approximately equal to the square root of K1 times K2 times F plus K1 times Kw divided by K1 plus F for our intermediate form. Now note that we need to account for the dilution of our base due to the addition of the acid in our value of F, our formal concentration. So our formal concentration is equal to the starting concentration of our base, our 0.1 molar, times our dilution factor, which is the starting volume of our base, divided by now the total volume, which is the volume of our base plus the volume of acid that we've added. And that then gives us a formal concentration of 0.05 molar. Now if we plug all those values in, then we get a hydrogen ion concentration of 3.16 times 10 to the minus 8, which gives us a pH of 7.50. Now note that the pH can also be found with this equation. That is, the pH is approximately equal to 1/2 times pK1 plus pK2. In other words, the pH is approximately equal to the average between the pKa1 and pKa2. Now, you might be tempted to think that this intermediate form, BH+, would make a good buffer because it can act as either an acid or a base. But you would be wrong. This is in fact the least buffered position on the titration curve. And the reason for this is because we have small quantities of our conjugate acid and conjugate base of BH+, that is, the BH2, 2+, and B, respectively. And that means that small additions of either acid or base will cause large changes in those concentrations of BH2, 2+, or B, respectively. So now let's look at point D. We again have a buffer here, but this time it's a buffer containing BH+ and BH2, 2+. That is between the intermediate form and the doubly protonated form. And this means that now we must use the pKa1. So we can again use the Henderson-Hasselbalch equation, where now we have to use pKa1, which gives us then a pH of 5.0. Now let's look at point E. This is then the second equivalence point. So we now have a solution that contains only our BH2, 2+, our doubly protonated form. And that means that we can treat this as an acid dissociation equilibrium problem. We know how to solve those. We just need to correct our formal concentration for the dilution that has occurred. There we get a hydrogen ion concentration of 5.72 times 10 to the minus 4, and the pH is then 3.24. Now after point E, this is then after the second equivalence point, the pH is then calculated by the volume of our strong acid added in excess. For example, suppose we have added 25.00 milliliters of our acid. In this case then the hydrogen ion concentration is the concentration of our acid, 0.1 molar, times the excess volume of acid, 25 milliliters minus 20 milliliters. We've gone 5 milliliters past the equivalence point, divided by then the dilution factor, so 10 milliliters plus 25 milliliters, our total volume of solution at this point, which gives us a concentration of 1.43 times 10 to the minus 2 molar, and then the pH is equal to 1.85. Now remember that some titrations of diprotic acids don't clearly show both of the equivalence point. That bottom titration curve that I showed is for the titration of 0.1 molar nicotine with 0.1 molar hydrochloric acid. Now nicotine has a pKb1 of 6.15 and a pKb2 of 10.85. And you can see the three different forms. We've got nicotine there, that's our base. Here's the intermediate form where we've added a proton on here to the nitrogen in the 5-membered ring. And then our doubly protonated form over here where we've added a hydrogen ion to both of our nitrogens, the nitrogen in the 5-membered ring and the nitrogen in the 6-membered ring. And again, remember that that second equivalence point is unclear. The first equivalence point we can see here at point H, but that second equivalence point at J, we just can't discern where exactly it is. And this is because BH2, 2+, is too strong of an acid, or alternately BH+, that intermediate form, is too weak of a base for the assumption that all of our hydrochloric acid added react to be true. Now instead of using an acid-base indicator, or in addition to using an acid-base indicator, often we will perform acid-base titrations while measuring the pH and plot the pH as a function of titrant added. So over here we've plotted the titration curve, and this shows the third and the fourth equivalence points for a hexaprotic acid titrated with sodium hydroxide. Now note here that our first and second and our fifth and sixth equivalence points are not discernible, even when we look at the first derivative and the second derivative. So again, note that at the equivalence point, the first derivative will reach a peak, and the second derivative will pass through 0. Now remember that the endpoint is the volume of titrant added where the slope of the titration curve is the greatest, that is, the largest value in our first derivative. Now the easiest way of finding that peak in our first derivative is to take the second derivative. That is, we can easily find the position of the peak in our first derivative by finding where the second derivative is 0. Because remember that the second derivative is simply the slope of the first derivative, and the slope at that peak must be 0. If it weren't 0, then some other point would be higher. So let's zoom in on the regions in the second derivative where it crosses 0. Now bear in mind that the volumes for which we have data are separated by some amount, and so we may need to interpolate between these existing data points. Now, the titration data near the endpoint are the least accurate because buffering is minimal and the electrode response is sometimes sluggish, and that means that sometimes we want a better method of determining the endpoint. And to do this, we use a ground plot. Now, a ground plot uses data from before the endpoint, usually starting somewhere around 0.8 or 0.9 times the equivalence volume up to the equivalence volume. And it uses that data in order to determine the endpoint. So let's look at an example involving the titration of a weak acid. Note that we must include the activity coefficients because the pH electrode measures the activity of the hydrogen ion, not the hydrogen ion concentration. So in this case, we have our acid dissociation reaction, we have our Ka expression, and that then has to account for the activities. So we have our concentrations, and we have our activity coefficients here. Now, before we reach the equivalence point, it's reasonable to approximate the moles of hydroxide ion added as the moles of HA that have been converted to A-. And that means if we titrate some volume VA in milliliters of HA with a formal concentration of Fa with some volume Vb in milliliters of sodium hydroxide with a formal concentration of Fb, that then means that the concentration of A- is equal to the moles of hydroxide added divided by the total volume, which is then equal to Vb times Fb divided by Vb plus Va. And that then means that the concentration of HA is equal to the initial moles of HA minus the moles of hydroxide added divided by the total volume, which is then Va times Fa minus Vb times Fb divided by Va plus Vb. Now we can substitute these expressions into our Ka expression, which we had here. So when we replace the concentration of A- with this guy, and we replace the concentration of HA with that guy, and then we do some rearrangement, we then end up with this expression. Now that term in parentheses on the right side of the equation can then be simplified because you know we have an FB up here and an FB down there, and so we can remove this VB term. So we now have VA times FA over FB minus VB, and then this first term is simply equal to VE, the volume at the equivalence point. And that means that then we can write the grand plot equation, which is VB times 10 raised to the negative pH is equal to the activity coefficient of HA divided by the activity coefficient of A minus times Ka times the quantity VE minus VB. And note that this quantity in parentheses here, the VE minus VB, is simply how much of our acid we have left. That is, how far are we from the equivalence point. Now, if we plot the VB times 10 to the minus pH versus VB, we then have a grand plot, and we get something that looks like this. Now, if that ratio between the activities is constant, then the slope of the grand plot will be equal to minus Ka times the ratio between the activity coefficients for HA and A minus with an x-intercept of VE. And in this case, you can see that as that line comes down, we have an x-intercept at a volume of 88.4 microliters. Now, note that the grand function never actually reaches 0 because 10 to the minus pH can never actually be 0. That is, as VB approaches VE, then our assumption that all of our hydroxide added reacts to form an equal quantity of A minus begins to break down. And that means that we ignore the nonlinear portion of the data and extrapolate from the linear portion. Now, another complication is that another source of nonlinearity is that the ionic strength will change as the titration proceeds, which then may cause the ratio between the activities to change. Now that was for the titration of a weak acid with a strong base. If we do the opposite and we titrate a weak base with a strong acid, the grand function then looks like this. And in this case then, the graph of VA times 10 to the plus pH versus VA is a straight line with a slope equal to minus the activity coefficient for B divided by the activity coefficient for BH plus, the protonated form, times Ka. And then it has an x-intercept of VE, our equivalence point. Now, we could also find the endpoint with an indicator. An indicator is an acid or a base that changes color under different pH conditions. That is, its various protonated species have different color. And the pH range over which the color changes is called the transition range of that indicator. So let's look at the example of phenolphthalein. Colorless phenolphthalein is at a pH of less than 8.0, and pink phenolphthalein is at a pH greater than 9.6. And the difference here is this proton there and this proton here are lost between a pH of 8 and a pH of 9.6. And that then changes the wavelength at which the phenolphthalein will absorb light from the pink region to then a region that our eyes can't see, which is why it's colorless. Now, we want to choose an indicator with a transition range as close to the pH at the equivalence point of the titration as possible. Now, the difference between the equivalence point and the observed endpoint of the titration is called the indicator error. Now, because indicators are themselves acids and bases, significant quantities of an indicator will alter the pH and the pH changes during a titration. So you only want to use very small quantities of your indicator. That is, you need an indicator that will absorb very strongly in the wavelength of interest. Now, some acids and bases, which are listed in Table 10.4, can be purified to be used as primary standards. Now, note that potassium hydroxide and sodium hydroxide are not primary standards because they contain both carbonate from atmospheric CO2 and adsorbed water. And that means that we must standardize solutions of potassium hydroxide and sodium hydroxide against a known quantity of a primary standard. But even after standardization, solutions have a finite shelf life before they must be standardized again. And this is because CO2 absorption will alter the concentrations of the bases, and evaporation, even from a tightly capped polyethylene bottle, can cause the concentration to change by about 0.2% at 23 degrees C. Now, strongly basic solutions will react with glass, and thus they should not be kept in volumetric glassware longer than necessary. And for an example of this, boiling a 0.01 molar sodium hydroxide solution in a glass flask for an hour decreases the hydroxide ion concentration by 10%. Most of the nitrogen-containing compounds in food are proteins, and that means that measuring the amount of nitrogen in food gives a rough estimate for how much protein there is in the food. Now note that this works because most proteins contain close to a 16% by weight nitrogen. Now, Kjeldahl nitrogen analysis is one method for measuring the nitrogen content of food. And this analysis involves digesting the sample in boiling sulfuric acid, thereby converting the amine and amide nitrogen into ammonium ion, and then oxidizing other elements present. That is, our organic carbon, nitrogen, and hydrogen get turned into ammonium ion, carbon dioxide, and water. Now, after digestion, the ammonium-containing solution is turned basic, and the ammonia that's liberated is steam distilled into a receiving vessel containing a known quantity of hydrochloric acid. That is, our ammonium ion will react with hydroxide ion to form ammonia gas and water. That ammonia gas is then reacted with a known quantity of hydrochloric acid to yield ammonium, and then the unreacted hydrochloric acid is titrated with a strong base in order to determine how much hydrochloric acid reacted with our ammonia. So now let's look at the leveling effect. In an aqueous solution, the strongest acid that can exist is the hydronium ion, H3O+, and the strongest base that can exist is the hydroxide ion, OH-. Now, if we dissolve an acid that is stronger than hydronium ion in water, then it protonates water to form hydronium ion. And similarly, if we dissolve a base that is stronger than hydroxide in water, then it deprotonates water molecules to form hydroxide ion. And these two effects combine to give us the leveling effect, which causes acids stronger than hydronium to behave as if they have the same strength as hydronium ion, and likewise for very strong bases, they behave as if they have the same strength as hydroxide ion. So let's look at an example. In water, perchloric acid and hydrochloric acid appear to have equal strength. That is, they are leveled to the strength of hydronium ion, because they will each react with water to form hydronium ion and then an anion, the perchlorate anion in the case of the perchloric acid, and the chloride anion in the case of hydrochloric acid. However, in acetic acid, the perchloric acid and hydrochloric acid no longer have the same strength. That is, the perchloric acid can react with the acetic acid to protonate the acetic acid, and the K value there is 1.3 times 10 to the minus 5, whereas hydrochloric acid can protonate the acetic acid with a K value of 2.8 times 10 to the minus 9. And therefore, the perchloric acid is a stronger acid with an acetic acid solvent. Now, why does this matter? Suppose we have a base like urea with a formula given here. The Kb is equal to 1.3 times 10 to the minus 14. Now that's too weak to observe an endpoint in an aqueous titration with a strong acid, such as perchloric acid. Now note that the reaction for this titration is then B plus the hydronium ion reacts to give us BH plus water. And note that the reverse reaction is more favored than the forward reaction is. But if we instead dissolve the base in acetic acid and then titrate with our perchloric acid, we now have this reaction where we have the bases reacting directly with the perchloric acid and not with the protonated acetic acid. And in this case then, the forward reaction is favored over the reverse reaction. Note that in this case, we're producing the ion pair here because the dielectric constant of acetic acid is too low for the ions to exist in solution separately. Now this reaction may have a large enough equilibrium constant to observe an endpoint in, and that means we can actually perform that titration, and if we can observe that endpoint, we would want to carry out that titration with acetic acid as the solvent instead of water. So now let's turn to calculating titration curves with spreadsheets. Thus far, we've used approximations to examine our acid-base titration, but we've seen that there are some conditions under which our approximations will fail. That is, if the concentrations are too low, the equilibrium constants are not of the right magnitude, or the Ka values of a polyprotic acid are too close together, as may happen in a protein, then things get more complex and we need to turn to Spreadsheet. We need computers to do the work for us. Now, suppose we titrate volume VA of acid HA at initial concentration Ca with volume VB of sodium hydroxide with a concentration of Cb, with VB of sodium hydroxide with a concentration of Cb. The charge balance is then given here, where we have the hydrogen ion concentration plus the sodium ion concentration is equal to the A- concentration plus the hydroxide ion concentration. Now note that the sodium ion concentration is equal to Cb times Vb divided by Va plus Vb. The formal concentration of the acid, given by FHA, is then equal to the concentration of the protonated form HA plus the concentration of the deprotonated form A-, which is then Ca times Va divided by Va plus Vb. Now remember that in section 9.5, we developed the fractional composition equation for A-, that is, the fraction of our acid in the deprotonated form, this alpha A-, is equal to Ka divided by the hydrogen ion concentration plus Ka. And we can now relate the A- concentration to the fractional composition. So the concentration of A- is equal to the fractional composition in the A- form times the formal concentration of HA, which is then equal to alpha A- times Ca times Va divided by Va plus Vb. And we can now substitute our expressions for the sodium ion concentration and the A- concentration into our charge balance, which then gives us the hydrogen ion concentration plus Cb times Vb divided by Va plus Vb is equal to alpha A- times Ca times Va divided by Va plus Vb plus the hydroxide ion concentration. And we can then rearrange this to get the fraction of titration for a weak acid by a strong base, symbolized by phi. So phi is equal to Cb times Vb divided by Ca times Va, which is then equal to alpha A- minus the hydrogen ion concentration minus the hydroxide ion concentration divided by Ca, all divided by 1 plus the hydrogen ion concentration minus the hydroxide ion concentration divided by Cb. And note that this equation now relates the volume of titrant, Vb, to the pH and a number of constants. That is, we will plug in a pH and we will then obtain the volume of titrant that gives us that pH. Also note that when this phi value here is equal to 1, then Vb is equal to Ve. That is, the volume of base that we've added is equal to the equivalence point. So let's use our equation to calculate the titration curve for 50 milliliters of 0.02 molar MES, which remember was our 2N-morpholino ethane sulfonic acid, which was a weak acid with a pKa of 6.27. And we're going to titrate that with 0.1 molar sodium hydroxide. Now note that the equivalence volume is 10 milliliters because the base is 5 times as concentrated as the acid. And we can now use a spreadsheet to calculate the Vb that gives us various pH values. Now note that we simply use trial and error to determine the starting pH that gives us a Vb equal to 0. And the book shows a very nice Excel spreadsheet of how to calculate this. It's got all the formulas that you need to type in. I'm not going to go through each individual cell and explain what needs to be there. You should take some time and familiarize yourself with this example. So suppose we titrate volume Va of acid HA at an initial concentration of Ca with Vb of weak base B with a concentration of Cb. Now let's denote the acid dissociation constant of HA as Ka and the acid dissociation constant of BH plus as KBH plus. Then the charge balance is the hydrogen ion concentration plus the BH plus concentration, which is equal to the A minus concentration plus the OH minus concentration. And just like in our last example, we can then say the A minus concentration is equal to alpha A minus times FHA, and alpha A minus is equal to Ka divided by the hydrogen ion concentration plus Ka. The formal concentration of HA is equal to the concentration of HA plus the concentration of A minus, which is then equal to Ca times Va divided by Va plus Vb. And we can write a similar expression for BH plus. If the acid were HA, then we would use the fractional composition equation to say alpha HA equals concentration of HA divided by FHA, which is equal to concentration of H plus divided by concentration of H plus Ka. But for weak acid BH plus, we can then say alpha BH plus is equal to concentration of BH plus divided by F BH plus, which is equal to concentration of H plus divided by the concentration of H plus K BH plus. And the formal concentration of BH plus is equal to Cb times Vb divided by Va plus Vb. And then substituting our expressions for the concentration of A minus and the concentration of BH plus into our charge balance equation and rearranging then gives us a phi equal to Cb times Vb divided by Ca times Va, which is equal to alpha A minus minus the H plus concentration minus the hydroxide ion concentration divided by Ca, all divided by alpha BH plus the hydrogen ion concentration minus the hydroxide ion concentration divided by Cb. Now note that the equations that are needed for calculating titrations using spreadsheets are summarized in Table 10.5. For the titration of a diprotic acid, phi represents the fraction of the way to the first equivalence point, and the second equivalence point is thus at phi equals 2. And that means that at phi equals 0.5, the pH equals pKa1. At phi equals 1, the pH equals the average between pKa1 and pKa2. And at phi equals 1.5, the pH equals pKa2. And that was acid-base titration.